All right, for VB and VC, those just have to be equal. Actually, this yellow so it stands out. These two have to be equal. They're touching. So if 1 meter travels here, then 1 meter travels here. There's no other way to do that. VB and VA, however, both of these things have the same VA, omega B and omega A is equal. But then because of the radius, right, then VB is going to be greater than VA. Because let's say, for example, in one rotation, B travels farther than A. Therefore, VB should be greater than VA. Omega B and omega C, we already determined, I'll do this two-part D up here, we already determined that VB is equal to VC. But remember that omega is equal to V over R. So omega B, if we compare omega B and omega C, that's going to be VB over RB, and that's going to be VC over RC. Okay, now you're going to get different things here because even though VB and VC are technically the same, right? Even though these are the same V's, R's are different because RB is equal to 2 times RC. So then when you plug that in, you get V over 2RC as compared to V over RC. And we see that this is true. Right, so basically we're finding like equivalence, right? VB is equal to VC, which is equal to V. So then V over RB and V over RC, these are equal to those things. And then since RB is 2RC, when you plug in 2RC for this, we see that we're going to get omega C this way. Now, if we think about this logically, the angular acceleration of the little one will be greater than the angular acceleration of the big one. Maybe, yeah, I think you can think that if the big one turns around once, the little one will turn around more than once. Because in one circumference of the big one, you're going to get more than one circumference of the little one, which makes the angular velocity of the little one bigger. Then the acceleration of B versus the acceleration of C. Well, we already can identify that, well, we can do the same thing by saying angular acceleration. You know what, let's just go with the linear acceleration of B and linear acceleration of C. Those should be equal because once again they're connected. So as one goes up, the other one goes up. However, this one, the angular acceleration or the linear acceleration of AB and AA, the linear acceleration of B versus the linear acceleration of A. When this thing starts spinning up, like their angular for F, their angular acceleration should be exactly the same because they're connected to the same thing. But angular I guess we can kind of do it this way, right? We can say angular acceleration is equal to A over R. So it's kind of like the same argument as over here. Because we can say that the angular acceleration of A will equal the angular acceleration of B, which just equals alpha. So then A is equal to alpha times R. A is equal to alpha times R. So this is RA, this is RB. Well, RB, these alphas cancel, and RB is bigger than RA. Right, so then it's going to be like this. So the angular acceleration, RB is bigger than RA. So the linear acceleration of B is bigger than the linear acceleration of A. That just makes sense, because if it accelerates from 0 to like 2 rotations per second, B had to go through a farther distance in the same amount of time. So there you go.